This is Unit 3, Block 4. We're going to talk about the second derivative, concavity of the function f, and finding inflection points on the function f. First of all, let's define what do we mean by the second derivative. So far in the course, we have defined the derivative. We've just called it the derivative, but another name for it really is to say that it is the first derivative of f of x. When I speak of the second derivative, which we often just refer to as f double prime, we are talking about the derivative of the derivative. The second derivative of f is the derivative of f prime. So there's two notations you might see for the second derivative. Notation would be f, and you see we have the 2. An alternate notation here, which we don't use so much in this class, but in a traditional calculus class we may use more often. We have the d and the exponent 2 to indicate second derivative. So df dx and df dx again. The change in y over change in x twice. I will not be using this much in the business calculus class. It's something that we would use more traditionally in a traditional calc class. So you will be using this f double prime notation, and the way you say it out loud is f double prime. All right, what do we do with this second derivative? Well, we're going to see that the second derivative will help us identify the concavity of the function f of x. It turns out that the sign of the second derivative, the sign of f double prime of x, will tell us the concavity of f of x. You need to have this at your fingertips. You need to understand this just as easily as you understand f prime positive means f is increasing. F prime negative means f is decreasing. Similarly, you need to understand f concave up means f double prime is positive. F concave down means f double prime is negative. Let's walk through it and see why this makes sense. So here in this example, I have 4 little sketches. I have here f increasing, and also we see f is concave up. And what we're going to do is just go through and sort out what would f prime look like and what would f double prime look like, or what do we know about f prime and what do we know about f double prime. First of all, f is increasing. So necessarily, as we've already learned, f prime, the slopes, are positive. Since f is increasing, f prime is positive. So if we were to draw an x-axis and we were to draw the graph of f prime, I know that the graph of f prime is entirely above the x-axis. F prime is positive. F prime outputs positive values. Now, also we see f is concave up. So if you think about the slopes of f, down here on the left side, maybe it has something like slope 1, right? The tangent line is going up, but it's rather shallow. As I walk further to the right, f is still increasing, but it's steeper. So if you drew its tangent line, it would have maybe slope 3, bigger positive number. And then as I walk even further to the right, f is still increasing, but it's even steeper yet. So perhaps it has something like slope 5. So on the graph of f of x, f prime is 1, then f prime is 3, then f prime is 5. All those f prime values are positive, but even more, all those f prime values are increasing. F prime 1, then f prime 3, then f prime 5. So when I draw f prime, it is positive, but it's also going up. F prime is positive, f prime is increasing. So here's a possible graph of f prime. It's above the x-axis and it's increasing. So let's now take this one more step. Now, if I think of f prime as my starting place, f prime is this graph I have, and I want to think about the derivative of this f prime graph. So here I have a graph that's above the x-axis and increasing. Because f prime is increasing, we know its derivative is positive. F prime is increasing, so f prime's slopes are positive. That means f double prime is positive. So whatever f double prime looks like, if you draw the x-axis here, I know for sure f double prime is above the x-axis. F double prime is positive. All right, so that was a lot of work to get to that point. I certainly don't want to have to go through that kind of reasoning every time I think about f and how it relates to f double prime. What I want to take from this is the following. F was concave up. That means f prime was increasing. The slopes of f were increasing, which means f double prime is positive. F concave up means f double prime is positive. Let's do it again. This time I have an example of a graph of f, but this time f is increasing, but f is concave down. So we have our little sketch here, an increasing concave down section of graph of f. Since f is increasing, we know f's slopes are positive. That means f prime is positive. But if we think about the actual values of those slopes, the actual values of f prime, over here on the left side of f, it's fairly steep. If you draw the tangent line, it's a line that is increasing and it's fairly steep. So maybe it had something like slope 5. As I walk a little to the right and I draw the tangent line again, the tangent line is more shallow now, maybe slope 3. And as I walk even further to the right, the tangent line is even more shallow, maybe slope 1. So all these slopes are positive, but as I walk from left to right, those slope values, those derivative values, are decreasing. Derivative value 5, derivative value 3, derivative value 1. So the derivative values are decreasing. F prime is decreasing. If I were to draw a graph of f prime, here's our x-axis, we know the graph of f prime will be positive. It will be above the x-axis, but it will be decreasing. So maybe something like this. Here is a graph of f prime. It's above the x-axis, but it's going down as we travel left to right. It's decreasing. So now the idea is we think of f prime, the graph of f prime, as our starting place. Here's a graph. It's above the x-axis. It's decreasing. And I ask, well, what do you know about its derivative, the derivative of f prime? Well, I know f prime is decreasing, so I know its derivative, f double prime, must be negative. F prime is decreasing, so f prime's slopes are negative. If I were to draw the graph of f double prime, here's the x-axis, I know f double prime is below the x-axis. Again, let's walk through that. We started with f. What I care about here is that f was concave down, which means its derivative was decreasing. F concave down, its slopes were going down, its slopes were decreasing, so f prime was decreasing, which meant the slopes of f prime were negative. F double prime is negative. If f is concave down, f double prime is negative. Okay, let's see if we can walk through that procedure a couple more times with our last two examples here. The last two types of graphs we could have. F decreasing, but f is concave up. That means f prime is negative, but f prime is increasing. So for example, on this graph of f, over here on the left, it might have slope -5. It's going down and it's fairly steep. Then as you walk to the right, maybe it becomes slope -3. And then as you walk further to the right, now it might be slope -1. The slopes are all negative. The f primes are all negative. But these values are increasing. -5, then -3, then -1. Those numbers are getting bigger, bigger, bigger. They're getting closer to 0. So the f primes are increasing. because f was concave up. Then, if you think about the graph of f prime, it's below the x-axis, but it's increasing. And from that, we now think of the derivative of f prime. Since f prime is increasing, we know f double prime is positive. So again, f was concave up, which means f double prime is positive. Lastly, f decreasing, f concave down. Since f is decreasing, we know f prime is negative. Since f is concave down, we know f prime is decreasing. Again, this would be like slope -1, then it gets steeper. Slope -3, then it gets steeper. Slope -5. Those slopes are decreasing. Going the next step, we find the derivative of the derivative. We find f double prime. Because f prime is decreasing, its derivative, f double prime, is negative. Making that final leap then, f concave down means f double prime is negative.